And this is my lab 3 over black hole and like star orbit and for physics 1. So for this lab, we use the gravitational force law, Newton's second law, and the momentum principle to model the orbit of a star around a black hole. And these equations are listed here. So we have the gravitational force law, so F grav equals G times R hat times mass of the star times mass of the black hole, which is m1 and m2, over the distance between them squared. And then we have dp equals F net dt, which is just final momentum minus initial momentum equals F net delta t. And then we have momentum equals mass times velocity. And from this, we also have to recognize, like, from this model, you can see the parallel and perpendicular forces acting on the star. They give you the total F net acting. And from all of these numbers that we find, we can put them into the gravitational force law and find the mass of the black hole. So this is my code for it. So in line to create the model. So in line 168 and 169, we find the change in velocity and the change in momentum, with change in velocity being v final minus v initial, and then change in momentum being p final minus p initial. And we get that dp dt, which is just delta p over delta t. And then we know from the momentum principle and like Newton's second law and everything that F net equals dp dt, because dp equals F net dt. So you just rearrange the equation. And then from that, we get we can find the parallel forces acting on the star. So that would be like p hat, which is just like the unit vector for the initial magnitude. For the initial momentum, which is p initial over magnitude of p initial. And then we can get d magnitude momentum over dt, which is just magnitude final minus magnitude initial over delta t. And then from that, if you multiply p hat by multiply those two numbers together, so p hat times d magnitude p delta t, you can find the parallel force. So we have F net parallel equals dp dt underscore par. And then from that, since we know that F net equals the parallel forces plus the perpendicular forces, because they add up together to give you F net, you can subtract the parallel force from the net force, and it gives you the perpendicular forces. And then from this, we use the gravitational force law to calculate the mass of the black hole. So you have like R, which is just the position between the star and the black hole, so which is just origin minus star position. And then from that, you plug it into the gravitational force law. And then we have our reference arrow, so we have like the position. I had to scale it down a lot because the forces acting on it are very, very large. So we have like our net force arrow, perpendicular force arrow, and parallel force arrow. And this is the code actually being run. So this is just a screen cap from the video. You can see, so this would be the orange arrow would be F net, the like pinkish purple arrow would be the perpendicular force, and then the blue arrow is the parallel force. And they all act together to give you F net, which is like pulling it towards the black hole. So after all this, we found the average mass of the black hole to be 9.3 times 10 to the 43. And you need to use the average just because there are so many data points, like, and you're refining the mass of the black hole every single time. There are like slight discrepancies, so I just like found the average of all of them, and then it gave me the F net and F perpendicular and F parallel average over the course of the thing. So net force versus change in momentum, they're calculated differently. Before this experiment, we used each other to find them. So like momentum is more related to like mass and velocity, and then from that you can find F net. So we just assume that they're equal for this model. And then if we use a different black hole, as long as the trajectory was the exact same, the mass of the black hole would be the same because the mass of the black hole is what caused it to be on the route that it was on. So as long as it went on the same route and like the same forces were acting on it, the same orbit, the mass of the black hole would have to be the exact same. Thank you.